Hello guys. In the previous lesson we have discussed about the how can we obtain the transfer function and state space representation of the wheel model. And so we obtain the SS form of wheel model without the breaking condition or the system design, and we have obtained the breaking system models in the wheel dynamics. And so we need to implement this state space form in the Matlab Simulink application. Okay, and so this is our editor or integrated development environment related to Matlab application. And so you don't need to use it, but if you are using it, and so this is easy to code anything in Matlab language. Okay, and so in order to create a Simulink model, we should choose these things, or we need to write the Simulink code, and the CRLF should be given to the program or the enter codings. Okay, and so if we are done with this, and we have the Simulink start page window in here, and so we need to choose the blank model or the empty model which is related to our project. And so we can create the model by pushing the left click on these things, and so we have the block diagram editor in here. Okay, and so we should set the model configuration parameters in here, and then we need to create a more efficient solver selection. And so the solver selection is set at the fixed step, and so we need to give the 1e-4 or the 0.1 milliseconds in the sample time processing. Okay, and so how can we create a model in the Simulink application? And so in order to create a configurable or the settable parameters, we should use the Matlab function block diagram in here. It's not an inefficient method for embedded systems, but if you are using the Matlab Simulink on the computer, then you can use freely this function. Okay, and so what about this function? This function name should be set to what? The wheel model. Okay, and so if we push left click double times, and so we have the function block in here. The return value of this function y, the input value of this function is u. Okay, and so in order to create a state space representation form, we should write it at the end of this code. The output session is that z dot must be equal to what? The a times z plus b times torque. Okay, and so this is our Matlab function block diagram or the system dynamics model in the derivative terms. Okay, and so if we save this file, we should proceed ver1 wheel models in here. And so if we can create these things, and so we need to get the output value should be equal to the z dot, and so we need to get the input value z. And so additionally I add the time parameter in here in order to create a reference signal or the torque value in that position. Okay, and so if we have this diagram, and then this function produce or generates the derivative term of our system like this one. Z dot is equal to what? A times z plus b times torque. And so if we have the derivative of the z terms, in which case we have the position and velocity value in the state variables, and so we need to put the integrator factor in here, because in the Matlab application we should convert this z dot value into the z1. Okay, and so if we put these things and link with the z, and so the loop is complete. Okay, and so if we have a function that generating the z dot value, and so we should use we can use the integrator factor in here, and so we get the integral of the z dot term, and so we obtain the z value at this time. Okay, but in our system matrix it's a 2 times 1 vector, and so we should set the integrator factor initial condition as the 0 0, because this things is represented by the Matlab program as a 2 times 1 vector. Okay, and so in order to obtain the clock value in the Matlab Simulink application, we can use the clocks. Okay, the clocks output the current simulation time, which is represented or showing in this section. Okay, and so we can use the z dot value in order to emulate or simulate our program to obtain the whole time response characteristics of our wheel model. Okay, and so we can write a specific codes in here like this one. The system matrices should be given at this position. And so what about this? We have two matrices in here, A and B. Okay, and so A must be equal to what? 0 1 0 0, and so we should give the 0 comma 0 and 0 0, and so this term is 1 because it's our dynamics dictate us. Okay, 0 1 0 0, and so in the second place we should set the B matrices in the first place, which is equal to the 0. Okay, and so we should give the program to 0 in here, and then in the second place R divided by what? M times R square plus J. Okay, this is our matrices. Okay, and so in order to produce the B and A matrices, in that case we should define the R value or M or J value in our programming language, which is included in this section. Okay, and so the system parameters can be given by R, for example, or assume that it's an arbitrary number, but the R is equal to what? The 0.1 meter. Okay, and so 10 centimeters is the radius of our wheel. Okay, and so M can be calculated by rho times V, and so if we have this kind of A and the white value is equal to what? For example 0.1, and so V is equal to what? The W times P R square. Okay, and so the rho value of this our wheel is equal to what? 10,000 kilogram divided by meters cube. Okay, and so the M is created by using both the shape parameters and the material properties. Okay, and so J is equal to what? The J, for example, in that case the inertia value of these things, suppose that the 1 in this case, and so it's arbitrary number, but in the following section or the lesson we will discuss about it, how to calculate in the correct form of these things, especially in the mill forming design. Okay, and so if we have this kind of systems in here, and so we can run this program, but the torque value is not created in here. And so for the torque value, or the input variable, can be defined by what? The torque in the first place should be equal to the 1. It's an arbitrary number also, okay? And so if we have this kind of systems in here, and then z dot gives us a x and x dot, or the position and velocity value of our wheel models. And so we should use the dmax value in here, and so this signal is split into the two parts. And so we need to add the scope value in here, and also a scope value should be added in here, okay? And so this is the position value of our code, and this is the velocity value of our code. And so the everything is okay, or if there is no syntax error in our code, then we should run this program like this one. And so the program is compiling and interpreted by the Matlab C compiler, and so we will have the results. And so there's no error in this time. And so if we check the position value of our code, we should set it down by like this, and so the position is increasing in the time, and so the velocity is the linear range of these things, okay? Because in our algorithm, torque is linear with the acceleration, and so this means that torque times some constants equal to the acceleration, okay? And so if we take the integration factor related to the acceleration, and then we obtain the velocity, and this velocity is linear, or with respect to the time. And so we can say that our code is correct because we don't have any damping ratio and spring factor of our systems, okay? And so what about this? The torque in the first place should be initialized by the 1, but we can functionalize this code like this one: bias plus amplitude times c omega, or not omega, and so the 2p f t value, okay? And so if we select the f is equal to the 0.1 hertz in here, and so amplitude value, which means that the sinusoidal amplitude can be given to this torque, okay? And so this is the 0.5, and so bias should be equal to, in the first place, is 0. And so this signal produce the sinusoidal signal with the amplification rate of the 0.5, or the magnitude of the 0.5, and so with the period of 2pf, or in the frequency domain 0.1 hertz should be given in here, okay? And so we can obtain also a torque value in the output session, and so torque can be generated by these things, and torque should be equal to this one, okay? And so we can observe the changing values in the torque value, okay? So the torque output. And so what about this? If we rerun this program, and then we have different position and velocity value in the output session, and so the torque value is given by the 0.1 hertz or frequency period, and so the 0.5 is given for the magnitude of this signal, okay? And what about the position value? The position value is given by these things. 0 to 10. And so this meaningful, but we cannot deduce the main result of this code by using this frequency value. And so I can pick a higher frequency range in this position, like this one, 1 Hz. Okay, and so if we rerun this program and then the position value given to this notation. And so what's our results on what's the outcome of this code? In the first place, the torque value is positive, and so this position is increasing, and so in this case the torque value is negative, and so this is the slowing down and constant term is given in here, and again and again this continues until the code is ended. Okay, because our period is 1 Hz and 2 Hz, 3 and 4 and 5. The general shape is has a repetition on this time variable. And what about the velocity value of these things? If we choose a positive torques in here, and so this torques increasing, but if we have the 0.5 seconds in here, if we have the negative torque value at this time, and so we reduces the velocity value of our wheel. Okay, and so if we have this kind of generosity or this kind of output, and then we can evaluate the time response of our section, because if we choose the torque in the correct form or inappropriate with any reference signal, such as if we choose the linear position tracking in here, or if we want to give this system or drive this wheel in the constant speeds, and so we need to choose the correct value of the torque, which is studied in the engineering approach, and we will call it the control theory. Okay, and so if we have this kind of system, and then we obtain this kind of parameters. And so how can we deduce, or how can we obtain the characteristics of this shape parameter and the material selection, or the mass spin damping ratio factor effective or effects on the system? And so if we have the J value in here like this one, and so if we choose the 1000 J value in here, and so if we rerun this program and then check out the velocity value, the velocity value is 16 times 10 over minus 6. And so in the previous case this is equal to the watt, and so we can reform this J value, and so the velocity value is 16 or 12 times 10 over minus 3. And so what's the outcome of this observation? The observation states that the torque value or the J value directly affects on the system time response in the time. And so if we have more velocity in the real life application, and so this J should be smaller than the normal one. And so if we have a small, or if we have a smaller velocity in the real life application, we should choose the J value in the form of the smaller than the normal one. Okay, and so if we have the great or the bigger J value, and then we have the small velocity, and so if we have the small, or if we have the small J value, we have the bigger velocity value in that case. Okay, and so what about this? If we choose the 1000th J value in here, and so also if we want to have bigger velocity value or the big velocity values, what can we do in this system? In this system, we should choose the torque value much more higher than the normal one, like this one. If we have in the J value 1000, and so the velocity value is the 16 times 10 over minus 6. But if we have the amplitude value of this torque value, like this one, is the 50. And so if we rerun this model, and then the velocity value is equal to 16 times 10 over minus 4. And so if we have higher torque value, like this one, 5000 Newton meter torque should be applied on this system, and then we will get what the velocity value is the 0.16 meter divided by second. And so what's wrong with the choosing of the J parameter in here? J parameter states that our system is slower if we choose the bigger J. And so if we want to use the J as the 1000, and so, and if we want to have the bigger velocity value in this case, and so we must to choose the amplitude value or the torque value is much more higher. Okay, and so this is the wrong condition, because we cannot produce in any car like these torques. 5000 Newton meter cannot be loading or cannot be produced by any standard car motors. Okay, and so we should optimize these selections, the J value and the torque value, okay, in order to create a reliable and considerable car design or the wheel design in the real life application. Okay, and so in this case we have designed the system parameters, and so you should notice that the position never turn the negative value, which means that the torque is applied on this wheel, but the energy is preserved in the mass factor or the inertia factor. And so if we have this kind of systems in here, and then we should put the braking system, because the wheel is going the infinity, because it's always increasing. But what about this? How can we slow down this dynamic? And so we can use the damping ratio or the braking system mechanism in order to slow down this system approach. In the next lesson we will talk about it, and we will design the most useful model in order to represent the wheel and the braking system in one system dynamics model, which was given by in this equation. Okay.